Welcome to this tutorial on batch normalization, a powerful technique that has revolutionized how we train deep neural networks. Batch normalization was introduced by Sergey Yaffe and Christian Szegedy in 2015, and it has since become a standard component in many state-of-the-art neural network architectures. Before we dive into batch normalization, let's understand the problem it's solving. Deep neural networks can be difficult to train, partly because of what's called the internal covariate shift problem. What does that mean? Well, during training, as the parameters of the earlier layers change, the distribution of inputs to later layers also changes. This means that later layers constantly have to adapt to new input distributions, which slows down training. Let me illustrate this with an example. Imagine we have a simple neural network with two layers. As we train the first layer, its parameters update, causing the output distribution to change. This changing distribution becomes the input to the second layer, forcing it to constantly adapt. This is internal covariate shift. Batch normalization addresses this problem by normalizing the inputs to each layer during training. This stabilizes the input distribution, making training faster and more stable. The normalization is done by subtracting the batch mean and dividing by the batch standard deviation for each feature across a mini-batch. Mathematically, for input x, we first calculate x normalized equals x minus mu divided by square root of sigma squared plus epsilon. Where mu is the batch mean, sigma squared is the batch variance, and epsilon is a small constant for numerical stability. After normalization, batch norm applies a scale and shift operation using two learnable parameters, gamma and beta. Y equals gamma times x normalized plus beta. This allows the network to learn the optimal distribution for each layer. Now, let's see how batch normalization is implemented in practice. In a typical neural network, a batch norm layer is inserted after the linear transformation, but before the activation function. Let's visualize this with a simple neural network layer. Without batch normalization, a typical layer would look like this: linear transformation followed by an activation function. With batch normalization, we insert a batch norm layer between these two steps. The batch normalization algorithm works as follows. 1. Calculate the mean and variance of the mini-batch. 2. Normalize the inputs using these statistics. 3. Scale and shift using learnable parameters gamma and beta. 4. Use this normalized and scaled output as input to the activation function during inference or testing. We don't have a batch of inputs. Instead, we use the running mean and variance computed during training. This ensures consistent behavior between training and inference. Batch normalization offers several important benefits that have made it an essential component in modern neural networks. First, it enables faster training convergence. By normalizing layer inputs, the optimization landscape becomes smoother, allowing for higher learning rates and faster progress toward the minimum. Let me show you a visualization comparing training with and without batch normalization. Notice how the network with batch norm converges much faster. Second, batch normalization has a regularization effect. Because each mini-batch is normalized slightly differently, this introduces some noise into the training process, which can help prevent overfitting. Third, it allows for training of much deeper networks. Before batch normalization, training very deep networks was challenging due to vanishing and exploding gradients. Batch normalization helps mitigate these problems. However, it's important to note that batch normalization introduces a dependency between samples in a mini-batch. This can be an issue for very small batch sizes or in online learning scenarios. Batch normalization is particularly useful in convolutional neural networks, CNNs. In CNNs, batch norm is applied across all spatial locations for each feature map. Consider a convolutional layer that outputs multiple feature maps. For each feature map, we calculate the mean and variance across all spatial locations and all samples in the batch. Then, we normalize each feature map independently. For a convolutional layer with output shape, batch_size, channels, height, width, batch normalization will have just two learnable parameters, gamma and beta, per channel, regardless of the spatial dimensions. This makes it very parameter efficient. Let's compare the impact of batch normalization on feature maps. On the left, you can see feature maps without normalization, which have varying distributions. On the right, after batch normalization, the feature maps have standardized distributions, making them easier for the next layer to process. To illustrate the impact of batch normalization, let's look at a real-world example. The original GNU/Linux architecture, while powerful, had training challenges. After adding batch normalization, the resulting BN inception network achieved better accuracy and trained much faster. Here's a comparison of the training progress between GNU/Linux and BN inception. With batch normalization, BN inception reached the same accuracy as GNU/Linux in just 35% of the training time. Additionally, the final top 1 accuracy improved by about 4%. This example demonstrates why batch normalization quickly became an essential component in deep learning architectures. Almost every modern CNN architecture after 2015, including ResNet, Inception v3, and DenseNet, incorporates batch normalization. Over time, researchers have developed several variants of batch normalization to address specific needs and limitations. Layer normalization normalizes across features for each sample independently, making it suitable for recurrent networks and transformers where batch size can be small. Instance normalization normalizes each sample and each feature independently, which has proven effective for style transfer tasks. Group normalization divides channels into groups and normalizes within each group, providing a middle ground between layer and instance normalization. There's also been some controversy about the initial explanation of why batch normalization works. While it was originally proposed to reduce internal covariate shift, recent research suggests its effectiveness might be more related to smoothing the optimization landscape and allowing larger learning rates. Let's conclude with some practical tips for using batch normalization in your projects. First, consider the placement. In most modern networks, batch norm is placed after the linear transformation, convolution, or fully connected layer, but before the activation function. Second, use an appropriate batch size. Batch normalization works best with larger batch sizes, typically 32 or more. With very small batches, consider using group normalization instead. Third, adjust your learning rate. With batch normalization, you can typically use higher learning rates. Don't be afraid to experiment with rates 5 to 10 times higher than you would without it. Fourth, reduce other forms of regularization. Since batch normalization has a regularizing effect, you might need less dropout or weight decay. Finally, remember that batch normalization behaves differently during training and inference. In most deep learning frameworks, you need to explicitly set the model to training or evaluation mode to ensure batch norm behaves appropriately. Batch normalization has been one of the most important innovations in deep learning, enabling the training of deeper and more complex networks that achieve state-of-the-art results across many tasks. Its stabilizing effect on training has made it a standard component in most modern neural network architectures, and understanding how it works is essential for any deep learning practitioner. While newer normalization techniques have been developed for specific applications, batch normalization remains the go-to choice for many computer vision tasks and general deep learning applications. Thank you for watching this tutorial on batch normalization. I hope this has helped you understand both the theory behind this powerful technique and how to apply it in practice.